This is Lab 5 for Physics 1, the free-for-all, in which I chose to study the space jump video. So the purpose of this lab was to look at the forces acting on this guy as he fell 39 kilometers through the atmosphere and see how that all comes together. So we have our force of gravity equation, force of drag equation, 1/2 rho, which is the density of air, times the drag coefficient, times the speed squared, times the cross-sectional area. And then, of course, we have our lovely velocity and position updates. And what we're going to see here is very, very simple. Just one object, two forces acting upon it, gravity and drag, both opposing. What we're looking is to hopefully see some terminal velocity point, some equilibrium between the two forces where it is no longer accelerating or decelerating. This is the video of it that I looked at. This is the URL at the bottom if you care to watch it yourself. There are also loads of other videos you can go see. This is now the computer model that I made up for it with a ton of assumptions and a ton of simplifications. Mass, I just searched up the average male mass, found it about 90 kilograms. For our coefficient of drag, B, I found that approximately while skydiving, when you go head first to create the smallest cross-sectional area, it's about 0.7. Air density, 1.293 kilograms per meters cubed. That is at sea level. And I was trying really hard to make this work where I could create some sort of function as a function of altitude against air density, but it just kept screwing up on me. So I decided to really simplify it down and stick with that 1.293 kilograms per meter cubed throughout the entire atmosphere. And also one other thing is that I calculated, if you look at my drag formula, I calculated the cross-sectional area of someone going head first to be about 0.0445 meters squared. So put it all together, calculate our gravity and drag, put them together, and then update our velocity and position, and just do that over and over. This is what it looked like here in the center as it fell. Those arrows are not to scale, as really the drag arrow should be smaller at the gravity than the gravity arrow at this point, as this is while it's still accelerating. I'm not sure what in the code was really making it do that. And then we have our charts for the y, position, and velocity over time here on the right, as there was no force that I was modeling in the x direction, no velocity, so that didn't really matter at all. We can see how they accelerated for a bit, and then quickly came to a terminal velocity point. Now, one issue with the model, and this is due to my air density issue in calculating drag and all, is that we cap out around a little over 200 meters per second, whereas the real deal, the guy, he got to a speed of about 370 meters per second. So the model has its limitations. However, doing some research on skydiving itself, 200 meters per second is definitely pushing the top end. So it's realistic in that manner. Certainly, though, that doesn't take into account the altitude that this guy was diving from. So from our discussion, I wanted to cover the energy going on here, because we have a lot of different forces and you're going to accrue a lot of energy falling from 39 kilometers up. So we have the work done by gravity here, calculated out about 34 million joules. However, we see that his kinetic energy at his top speed was only 6 million joules. So we have this difference of 28 million joules. Well, we got to factor in drag. So we calculate that, and that's only a paltry 500,000 joules. So still, we're over 27 million joules in the difference. Well, where does that go? Well, that's going to go to heat, and that's going to heat his body up. Now, the human specific heat capacity is about 3 kilojoules per kilogram. And so calculating that out, we would find that his body raised to a temperature of 139 degrees Celsius. However, of course, he had a suit, and that's going to absorb some of the heat too.